What specific problem does the SuperBPE method aim to solve in the context of tokenization for language models? And what gaps in existing research does it address?
The SuperBPE method aims to solve the problem of inefficient tokenization in language models, LMs, by introducing a two-phase tokenization process that allows for the learning of both subword and superword tokens. Traditional byte pair encoding (BPE) tokenization restricts merges to whitespace separated chunks, which can lead to suboptimal tokenization and fails to capture multi-word expressions that function as single semantic units. SuperBPE addresses this gap by initially enforcing subword learning through whitespace per-tokenization and then transitioning to superword learning, enabling the tokenizer to discover common word sequences as single tokens. This approach not only improves encoding efficiency, but also enhances model performance on downstream tasks, as evidenced by the significant improvements observed in models trained with SuperBPE compared to those using standard BPE. Additionally, SuperBPE fills a research gap by demonstrating that tokenization can be optimized beyond subwords, which has been inadequately explored in prior work that often resulted in mixed effectiveness.
How does the proposed SuperBPE algorithm work? Please illustrate it step by step, detailing both the per-tokenization curriculum and the transition from subword to superword tokens.
The SuperBPE algorithm operates in two distinct phases to enhance tokenization efficiency. First, it begins with a per-tokenization curriculum where whitespace per-tokenization is employed to enforce the learning of subword tokens, mirroring the conventional byte pair encoding (BPE) approach. This initial stage continues until a specified vocabulary size, referred to as the transition point, T, is reached. In the second phase, the algorithm disables whitespace per-tokenization, allowing the tokenizer to learn superword tokens that bridge across whitespace, thus enabling the combination of subword tokens into more semantically cohesive units. This two-stage process not only improves the vocabulary's encoding efficiency, but also allows for the discovery of common multi-word expressions, resulting in a more effective language model overall.
Can you provide a simple example that demonstrates the inner workings of SuperBPE? Walk through the algorithm steps with the example to highlight how tokens are generated during the two-stage training process.
To illustrate the workings of SuperBPE, consider the phrase "by accident." In the first stage of the SuperBPE algorithm, per-tokenization occurs with whitespace as a delimiter, resulting in the initial tokens by and accident. This stage mirrors standard BPE, where the algorithm learns subword tokens without merging across whitespace. Once the transition point is reached, the second stage begins, where the per-tokenization step is skipped. Consequently, the algorithm can merge the tokens by and accident into a new superword token by accident, allowing the tokenizer to treat this multi-word expression as a single semantic unit. This two-stage process enhances encoding efficiency by enabling the discovery of common word sequences while still establishing a foundational vocabulary of subwords.
What are the theoretical or practical benefits of using SuperBPE compared to traditional BPE tokenization? Discuss specific improvements in terms of efficiency, accuracy, and computational resources.
The SuperBPE tokenization algorithm offers several theoretical and practical benefits over traditional BPE tokenization. Firstly, SuperBPE enhances encoding efficiency by producing shorter token sequences, which leads to a significant reduction in bytes per token. It achieves better performance with a smaller vocabulary size compared to BPE, reaching 55 bytes per token at 50K vocabulary size, while BPE plateaus around 45 bytes per token at 200K. Secondly, SuperBPE improves accuracy as evidenced by a consistent +4.0% performance increase across 30 downstream tasks, including notable gains of +8.2% on MMLU and winning on 25 out of 30 tasks. Additionally, SuperBPE is 27 to 33% more efficient at inference time, which translates to lower computational resource requirements during model deployment. Finally, The method's two-phase training process allows for the effective learning of both subword and superword tokens, enabling the model to capture multi-word expressions as cohesive semantic units, thus improving overall language model performance without necessitating changes to the model architecture or training framework.
How was SuperBPE validated and tested within the experiments? Describe the datasets used, the benchmarks for performance, and the metrics that were applied to demonstrate the algorithm's effectiveness.
SuperBPE was validated and tested through a series of experiments where models were pre-trained from scratch while fixing the total training flops and vocabulary size, with only the algorithm for learning the vocabulary being varied. The training utilized a 10 GB subset of OLMo2's pre-training corpus, and the models were evaluated on 30 benchmarks covering various domains such as knowledge, math and reasoning, coding, reading comprehension, common sense, language understanding, and string manipulation. Performance was measured using task-specific metrics, with the strongest SuperBPE model achieving an average improvement of +4.0% over the BPE baseline across these tasks, winning on 25 out of 30 individual tasks. Additionally, bits per byte, BPB, was used as a metric to evaluate language modeling performance, normalizing the loss by the encoding efficiency of the tokenizer. The experiments demonstrated that SuperBPE models consistently outperformed BPE models, particularly excelling in multiple-choice tasks with a performance improvement of +9.7%.
What specific results were achieved using the SuperBPE method in the experiments? Include details about performance metrics on downstream tasks and any significant findings from the analysis.
In the experiments, the SuperBPE method achieved a notable average improvement of +4.0% over 30 downstream tasks compared to the BPE baseline, with the strongest SuperBPE model, transition point t equals 180K, winning on 25 out of 30 individual tasks. Specifically, it excelled in multiple-choice tasks, showing a performance increase of +9.7%. The SuperBPE models were also found to be 27 to 33% more efficient at inference time than their BPE counterparts. Analysis revealed that SuperBPE tokenizers produced segmentations that corresponded more closely to multi-word expressions, leading to a more even distribution of segmentation difficulty. Additionally, while the SuperBPE model had a slightly higher normalized language modeling loss, bits per byte, than BPE, it consistently outperformed BPE on challenging downstream tasks, indicating that it effectively captured complex semantic units.